So last time we talked about some properties of probability. One property of probability that you may not have discussed in undergraduate courses is the continuity of probability. So consider a sequence of events AI, such that this is an increasing sequence of events where A1 is a subset of A2, A2 is a subset of A3, and it goes on like this indefinitely. Okay, let's define a set A as the limit of the sequence, such that the set A includes all the sets in the sequence. What does this infinite union mean? This infinite union essentially is the limit as n goes to infinity of a finite union from 1 to n. Okay. Now, the continuity of probability is a theorem that says that, well, then the probability of the limiting set is equal to the limit as n goes to infinity of the probability of the sets an. How can we prove this? Well, we can always express the set A as A1 union A2 difference A1 union A3 difference A1 A1 union A2 and so on. Okay, but because of the fact that the sets are increasing, A1 union A2 is nothing but A2 itself. So then we have a simplified expression where in each term we have the difference from the previous set in the sequence. A4 difference A3, etc. So then the sum is nothing but, by the additivity property of probability, this is nothing but the P of A is nothing but the limit as n goes to infinity, summation I from 1 to n, P of AI difference AI minus 1, essentially, right? And not essentially, but exactly, where let's define A0 as the empty set, if you will. Okay, then. But what is this? Now, this can be expressed as P of AI minus the probability of AI intersection AI minus 1. Okay. But AI intersection AI minus 1 is nothing but AI, so this is simply probability of AI minus 1. Okay, but then this whole thing is a telescoping summation, and therefore we have the limit as n goes to infinity of P of an, and we're done. Okay. Now you can show the same continuity property of probability for a decreasing sequence of sets, such that if B1 is the largest set in the sequence, and the sets keep shrinking up to infinity, then the probability of the limiting set as n goes to infinity, intersection bi, I from 1 to n, can be found by taking the limit of the sequence of probabilities. Okay, and can prove it in a similar way, but basically you can do it by taking complements, if you will, if you wish, in the proof here. Okay, now next we'll define a very important concept in probability, which is independence. Okay, so definition. Two events, A and B, defined on the same probability space, are independent if and only if probability of A intersection B is equal to probability of A times probability of B. Okay, in general, a group of sets, in general, a group of sets A1 through AN are independent. A group of events A1 through AN are independent if the probability of the intersection of an arbitrary group of sets is always equal to the product of the probabilities of the sets in this group. For all groups of sets, meaning for all subsets S of subsets of indices 1 through n. Okay, so basically, how many conditions would we have to check here? We would need to check, well, there are 2 to the n possible subsets S, but one of the subsets is empty. There's nothing to check there, and one of the n of the subsets are simply have 1 elements. So 2 to the n minus 1 conditions need to be satisfied for n events to be all independent of each other. Okay, so some corollaries of this definition are, first of all, when 2 events are disjoint, they cannot be independent. So in other words, if P of A and P of B are non-zero, and A and B are to be independent, then A and B cannot be disjoint. Okay, why? Because P of A intersection B is P of A times P of B, but if these are non-zero, the product cannot be 0, so the probability of the intersection has to be positive. This means the intersection is not empty. So I will emphasize this again. Disjointness of 2 sets implies that they are dependent. So disjointness implies dependence. And disjointness is in fact a very strong form of dependence, because it says that if A happened, B cannot happen. Okay. Secondly, if the probability of B is positive, okay, and A and B are independent, then the probability of A given B must be equal to the probability of A. Now, why is this true? Let's remember the definition of conditional probability. Probability of A given B is equal to, probability of A intersection B divided by the probability of B. Okay? Well, But if they are independent, this breaks down into a product, and we can always cancel out P of B because it's not 0. So this is true. All right. Now, incidentally, now that we wrote this, it's a good time to also note Bayes' rule. Bayes' rule is a way of changing the order of conditioning such that if the probability of A and the probability of B are both non-zero, the probability of A given B is given as the probability of B given A times the probability of A divided by the probability of B. Well, this is trivially true because of the definition of conditional probability, because by the definition of conditional probability, this is equal to probability of A intersection B. So that's Bayes' rule. And we will use this a lot, especially in conjunction with the total probability theorem in many probability problems. Finally, A and B, two sets A and B, are conditionally independent. Okay, if let me see, are, let's say, conditionally independent, conditioned on an event C, if the probability of A intersection B given C equals the probability of A given C times the probability of B given C. Now, conditional independence does not imply independence. Similarly, two sets that are independent may become dependent once they're conditioned on another set C.